So in the first two videos of the stuff on derivatives of logs and logarithmic differentiation, in video 1 we talked about the derivatives of logs. Sorry about that, let me turn the volume off. In the first one we talked about derivatives of logs. And derivative of logs, the first thing that I did is I proved to you that the derivative of natural log x was 1 over x. Okay? By extension, we then talked about how the natural log of u is u prime over u, where of course u is understood to be some expression in terms of x. Then we used some properties of logarithms to not talk about log base e, but log base a, so any other base besides the natural base. And we wound up with x natural log a in the denominator instead of just x. And of course, just one more, by extension, log base a of u winds up being u prime over u times natural log a. And that gives us the derivative of any function that involves logarithms. Okay. And therefore, it might come in combination with other rules like the product rule or the quotient rule or something like that. But these are kind of the four possibilities, right? Either your logarithm is based e or your logarithm is based something other than e. Either it's the logarithm of just the variable or it's a logarithm of an expression in terms of your variable. So this is regular, this would be chain rule. This would be regular, this would be chain rule. So here are your four things that we needed to use. Now, all of this needs to be understood in the context of the properties of logarithms, which also sometimes apply. And I'll flesh that out a little bit more when we get to some examples. Now, derivatives of logs is to be distinguished from logarithmic differentiation. These are what you use when you're given a function that happens to have a logarithm in the function itself. Logarithmic differentiation is instead something that you use when you actually are sort of artificially imposing logarithms on an existing equation in order to help break it up, right? And that helped us to arrive, and using that helped us to arrive at an explanation of why the derivative of e to the x is e to the x, right? Because I took y is equal to e to the x, took the natural log of both sides, differentiated implicitly, and went forward from there. So, and of course we extend it to the chain rule where it's not e to the x, but it's e to some expression in terms of x, which we often call u, and this becomes e to the u, u prime, or du dx, or whatever you want to say. Now, we also used this particular method to find not just the natural base, but any base exponential. And it winds up being a to the x times natural log a. And of course, when you then extend that to the chain rule, a raised to an expression in terms of u, you get a to the u times natural log a times u prime. Now those were, and of course they're all related, but those were the four new rules in terms of logarithmic differentiation and four new rules in terms of exponentials that we arrived at from logarithmic differentiation. So derivatives of logs, logarithmic differentiation. Now this isn't logarithmic differentiation, these are sort of conclusions that we came to as a result. Logarithmic differentiation refers to, of course, the strategy employed of imposing a logarithm from without. So from there, now that we've sort of used that as an excuse, so sort of the beginning of video 3 is an excuse to review that stuff, let's go ahead and jump in with some examples. So we have y is equal to the natural log of sine x plus 1. Now, of course, I would probably prefer that be the natural log of 1 plus sine x, so that there's no ambiguity, right? There's no ambiguity as to whether the plus 1 is part of that angle measurement or not, because sometimes y'all get a little bit fast and loose with your use of parentheses and fail to put them where they should be, or recognize them where they aren't, or all sorts of fun stuff like that. I would prefer that this be written like this, but whatever. So we want to differentiate with respect to x. We recognize the fact that this is indeed a derivative of a log, okay? This is natural log u, right? It's just that this right here is your u. That is your expression in terms of x rather than just being the variable itself. So what we know is that this winds up being 1 plus sine x because u goes in the denominator here, and then the derivative of u goes in the numerator. Well, what's the derivative of 1 plus sine x? Well, it's 0 plus cosine x, and that right there is your derivative, okay? Now, that is relatively straightforward. Let's look at another example. How about y is equal to the natural log of t times 5 to the t? And you think to yourself, oh gosh, that's disgusting. We're probably going to have to do something like, t times 5t, and then I have to do the derivative as the product rule up here. And so it's the first times the derivative of the second plus the derivative of the first times the second. But let's not do that. Now that's true, but we've forgotten something very, very crucial, which is the fact that this breaks up like that by properties of logarithms. Okay? So this right here is true, but unnecessary. Why in the world would you do it that way? Unnecessary, okay? True, but unnecessary. This is one of those stop, think, which means applying simplification, usually, simplification methods that we know, to here. Now, this is natural log t. That's easy enough. This is t with a numerical coefficient. So that second term is actually linear. Now sometimes we fail to recognize that because natural log 5 isn't exactly 2, right? But if you plug natural log 5 into your calculator, you get a value. That is a numerical value, and therefore it is the functional coefficient of that linear, that first degree variable. So actually, that should be y prime. So y prime just winds up being 1 over t times natural log 5. And actually, if you were to break that apart into two separate fractions and simplify it, you would get exactly that. But how much easier is it once you've simplified according to the rules of, or the properties of logarithms, to go straight to there, okay? Now that since we're talking about ones where you can simplify, let's go ahead and do e to the natural log x squared. And you're like, oh my gosh, that's ugly. Well, isn't that just e to the 2 times natural log x? Okay, well, isn't that e to the natural log x squared? Okay, well, isn't that then x squared? How much easier is that, right? Because that's just 2x. Now from here to here, I use properties of logarithms to take the exponent down, okay, to here. Now, is that legitimate? The answer is no, okay? This is an illegitimate one because we get overzealous sometimes in terms of simplification, okay? That is not the case, because remember, natural log of x squared is not equal to the natural log of x squared. This one simplifies into 2 natural log x. This one does not. So this one winds up being, this is e to the u, okay? So there's e to the u times u prime. So u prime is just 2 times natural log x times 1 over x. That is your derivative. Okay? So that actually is kind of ugly. So that just, basically the difference between y is equal to e to the natural log x squared gives me y prime is equal to 2x. How simple is that, right? But this is the derivative of the function that I was actually given, okay? And so we need to be careful to stop and think in order to simplify, of course, before we do. But we need to be very careful that we're not being overzealous in doing so. Now, is it absolutely necessary to simplify this one? No, you actually could. You know, this is an easy enough one. That's 2x squared plus 11x plus 9. And so you could go from here to y is equal to 4x plus 11 over 2x squared plus 11x plus 9. Okay, and that's y prime, okay? But you could just as easily split this apart. Now this is easier, but not much easier, right? Because I mean, remember that the logarithm of a product winds up being the sum of two logarithms. And therefore y prime is 1 over x plus 1 plus 2 over 2x plus 9. Well, I got news for you. If you were to actually get a common denominator and push this together, you would get this. If you were to perform the decomposition into partial fractions of this expression, you would get that. They are synonymous. Okay, they are one and the same. It's just a matter of, this is one of those judgment call ones where you don't have to use the properties of logarithms to simplify, but it might actually be a good idea. But there was one thing you really don't want to do, is to leave it in its factored form and to do it this way, because then you have to do the product rule in the numerator, and who the heck wants to do that? So that is a couple of problems using what we know about derivatives of logs, primarily. I mean, we did a little bit of exponential up here. Let's now do a couple of examples involving logarithmic differentiation. Now, the first category of equations that benefit from this are the ones where it is useful but not absolutely necessary. Can you differentiate that from this form, the form that's given? Yeah, you can. It probably is not the best idea to do it that way. You know, in order to do it, I would probably, you know, x cubed plus x, and then x plus 1 to the 1/2, and then, of course, you have, you know, chain rule inside of the quotient rule and all sorts of fun stuff like that. I would not do it that way, though, especially if you know what you're doing with the derivative next doesn't require it to be in a single rational expression. You can actually wind up with something a little bit nicer, and I'm going to go ahead and put this in terms of a fractional exponent right now. If we take the natural log of both sides, because I know that this winds up simplifying into that, right? Where all of the factors in the numerator become positive logs and all the factors in the denominator become negative logs, with that pushed out in front. And then we simply have to differentiate term by term. And then we just have to multiply both sides by y. Y meaning that expression right there, the x expression that is equivalent to y. And there we go. Okay? We'll continue on in the next video with more examples of logarithmic differentiation, but that's the first category of things that we use logarithmic differentiation on. Okay?